In this lesson, we're going to be talking about solving for electric field strength and then drawing electric field lines around point charges and non-point charges as well. So if we remember from the last lesson, to solve for the electric field strength, we are going to take the electrostatic force and divide it by some Q. Okay, where this is Q1 or whatever, this is the Q inside the field. And this is the electrostatic force. And we can't forget that sometimes we're going to have to solve for that electrostatic force and plug it into here, but that's fine. We're going to know that this electric field can be solved for. All right, so don't confuse electric field strength with Fe, which is the electrostatic force. So let's look and see how we could solve a problem for that. Calculate the magnitude of the electric field strength at a point in the field where an electron experiences a force of a magnitude of 1 times 10 to the minus 15th Newton. So let's write down some givens. In this problem, one of the things that's given is Fe. All right, and that's experiences a force with a magnitude. So that's this, 1.0 times 10 to the minus 15 newtons. Also given, okay, they tell you this electron. Guys, electron, you know the Q of an electron is 1.6 times 10 to the minus 19th coulomb. So we know Q. And what they want you to solve for is calculate this. So when you're solving for this, you're going to be looking for this phrase right here, which is going to tell you that you are solving for capital E. So we look at the formula. Very simple. Fe over Q. We could substitute into that formula now. All right, and yes, this is an electron, but we're just looking at the magnitude right now. So we see that the E, when we do some fancy math, is going to come out to 6.3 times 10 to the third newtons per coulomb, which is the unit for electric field strength. It's really as simple as that. Where things can get a little bit more confusing is drawing electric field lines. All right, and this is going to happen first amongst point charges. So what a point charge means, I just have one charge right here. On this side, example 1, we'll say that we have some proton here. And example 2, we'll put a minus sign here. So this is one positive charge, and over here is another point charge. Now, around this, just like on Earth, we are going to see electric field lines. And they will be the same around each. But there is one major difference, and that is the direction of the field. So I'm going to look at this right here, and I'm going to tell you right now that for a positive charge, the electric field strength points away. And for a negative charge, the electric field strength points inward. And this will always be the case. Electric fields always point to negative. All right, and I remember this is saying put the coin in the slot. And electric fields always point away from positive. And you might hear this referred to as, the path that a positive test charge would follow. And really all that means is that if you need to know the direction of an electric field, you will picture what a positive charge would do. Okay? So if I had a point right here, I would ask, what would a positive do? A positive would go like this. Therefore, that is the electric field direction. Okay? So sometimes they won't tell you what is inside the sphere. So if I gave you a charge right here and I said that's some charge, and around that some charge there was an electric field like this, I could say, what is the charge of Q? And you would know that the answer to that question is it's a negative charge. Why? Points inward. And positive attracts to negative. So if I put a positive here, what would a positive do? A positive would go like this. If I put a positive here, what would a positive do? A positive would do like this. So anywhere I put a positive, that's what I'm going to do. And when they ask you to draw an electric field line, think, what would a positive do? Okay, and that's, if you do that, you'll be good to go. Now sometimes there's going to be two charges near one another. All right, so let's look at the first one. Let's say I put a positive near a negative. Well, now there's going to be an interaction between these two. Same thing though, what would a positive do? If I needed to draw the electric field line through this object, I would say that it was going to travel from here right across to here. But then if I put a positive here, it's going to want to kind of do this, but it's also going to be getting dragged down towards this. So what's going to happen is we are going to have this situation where the field line actually bends. All right. And around it where there's no other interaction because there's no other positives over here, it would act just like a point charge, but in between, there's going to be this bending, okay? And we need to know, and this is very, very, very important, field lines never intersect, okay? So you would never see a situation like this. You see how they're touching right there? No good. Okay. So what would a positive do? If I put a positive here, it would it would be pushed away from here, and then it would be attracted into here. All right. Now, what if they were the same charge? Well, now instead of going from here over to here, what would happen is it would be repelled, but then it would meet the field from here, and we'd get some sort of asymptote here like this. All right, and the field lines would bend upward, away, because they'd both be attracted away. What would a positive do? A positive would attract away from here. All right, and a negative would just do the same exact thing, same exact field lines, but now that asymptote comes in. And the last thing that you're going to need to know the electric field around is two plates. Let's say I have a plate up here. This is plate 1. And this is another plate down here. Let's call this plate positively charged. And this negatively. The electric field between these two plates will still do the same, but now they'll travel straight down. Straight up and straight down. All right. And the one last thing that I want to talk about these electric field lines, guys. Let's go back to this point charge, positive. What would positive do? It would go away. Okay. Electric field strength is only dependent on distance. Okay. Super important. Meaning this. If I put 3 charges here, if I have a charge A, B, and C. All right? It's a common misconception that this one will be the strongest. This is not the strongest field. This is. Because of this, all right? Just because it's on the line does not mean that it is strong. All right, so this is like that. On the line does not mean strong. All right, guys, that should get you where you need to go. Check out the questions. Next lesson, we'll talk about something a little bit different, but I hope that gets you there for today.